In this video, we'll have a short discussion about Fermat's theorem. So Fermat's theorem has to do with local maxes and minimums. It says if you have a function with a local max or a local min, like the one I have drawn here, so let's first identify. It looks like we have a local max, and in this case we actually have a local min as well. So it says if your function has a local max or a local min, and if the derivative exists, then you should know the value of the derivative at those points. So think about your tangent line. Notice that at the local maximum, if the derivative exists, then that tangent line is horizontal, so the slope must equal 0. And the same is true here at this local minimum. The tangent line would be horizontal, so the slope must equal 0 at both of those points. So if f of x has a local max or local min at c, and C, I can label that on my graph here for you. C would be the x value where the local max occurs, or the x value where the local min occurs. And as long as the derivative at C exists, so it is differentiable there, then we know that f prime of C, the value of the derivative, must equal 0. So if you have a local max or a local min at C and you know that the derivative does indeed exist, then you know the value of the derivative must equal 0. So that's Fermat's theorem. Now let's look at the converse of Fermat's theorem. So to create the converse, what you're going to do is you're going to interchange what we call the hypothesis and the conclusion of this theorem. So in this theorem, the hypothesis is the if portion. If f of x has a local max or a local min at C and the derivative exists. That statement is called the hypothesis. The conclusion is the then portion. So then f prime of C is equal to 0. So if we interchange what I have highlighted in yellow and pink, we interchange these, we have a new statement, and that new statement is called the converse. So the converse would say if the derivative is equal to 0, then there must have been a local max or a local min. And we need to think about whether or not that statement is actually true. So let's draw some graphs and think about it. If the derivative is equal to 0, are we guaranteed to have a local max or a local min? And if you take a look at kind of a common cubic curve, that will probably answer the question. If we were analyzing, let's say, like y equals x cubed. If we were going to take a look at the value of the derivative here at this point, which is called the inflection point. So the value of the derivative here would be equal to 0 because we would have a place where the tangent line is horizontal. However, this point is not a local max and it's not a local min either. Therefore, is the converse going to be true? The answer here is going to be no. Okay, so what you need to get out of this is an understanding that just because the derivative is equal to 0, that doesn't mean that you automatically have a max or a min. If the derivative is equal to 0, all that tells you is that you have a nice horizontal tangent line. That's it. We're not guaranteed that we have a local max or local min just because the derivative is equal to 0.